First of all, let me correct something that was up here. For some reason or other, I'd managed to put a 2 on there, which shouldn't have been there. So if you're making notes, that should just have been a single hydrogen atom. Okay, so what we're going to do now is just have a look at some NOx chemistry. As I said, we need to understand NOx chemistry because we want to control NOx emissions. And so we're going to look at 3 reactions that are important in, first of all, in NOx emission, but then in NOx control. And they're just single elementary reactions that have got high sensitivities and that have led to all sorts of interesting issues relating especially to the products that are formed. So let's move on. So we're going to look, first of all, at mechanisms for forming NOx, and then examine these 3 reactions, CH plus N2, which is involved in something that's called prompt NOx formation, NH2 plus NO, which is involved in a method of NOx reduction, which is called selective non-catalytic reduction, and then HCCO plus NO, which is involved in another mechanism, another approach to NOx reduction called Reburn. Okay, so mechanisms for NOx formation. There's something called prompt NOx. So Fenimore observed NO formation in the primary reaction zone of a flame, and he attributed it to a reaction of a hydrocarbon radical with N2 and suggested this reaction here, CH plus N2 going to HCN plus N. For fuels like coal, then there is nitrogen present in the fuel, and so this reacts and also generates HCN, and the route from HCN to NO was discussed, if you want to look at it, by Miller and Bowman in this paper here. And another mechanism is a high-temperature mechanism called the Zeldovich mechanism involving reactions of this sort. So we're going to look at this particular reaction here, or we're going to look at CH plus N2. So this is taken from that paper by Miller and Bowman and shows how this reaction, CH plus N2, leading to HCN, can then lead to NO formation. So HCN reacts with O to form NCO, NCO reacts with H to form NH, and that reacts with H to form N, which can then react with OH to form NO down here. Or alternatively, it can react with NO to form N2 plus O. So complicated mechanisms, but key to it was this initial reaction here, CH plus N2 forming HCN. And this is an evaluation for CH plus N2 by Bolch et al., measurements in the high temperature regime, and this was the evaluation result that came out of it. In addition, there is a reaction in which CH reacts with N2 to form this species CHN2. So we need a third body, and we're stabilizing to form CHN2 plus M. And so these are lower temperature measurements and looking at the pressure dependencies of the reaction. But this is not important in the higher temperature regions that we're talking about. So we're not interested in the pressure-dependent reaction. We're interested in the pressure-independent reaction. This is a paper that came out in 2000 that made theoretical calculations on what was going on. And so CH reacts with N2. As we saw in that earlier slide, there's a significant activation barrier, and it forms this first intermediate, which is That's a nitrogen CH that can isomerize to this similar intermediate here with a different structure. And then the idea was that this reaction then occurs and eventually forms HCN plus N. But for that to occur, what has to happen is that one of the things that this species can do is the nitrogen atoms can move around and form this species, which can then dissociate to form NCN plus H. If we're going to form HCN plus N, which is the proposal, then what we've got to do is we've got to move over into this part of the potential energy surface. Now, there are problems with this for these arguments that we made up here. If you look at the nitrogen atom, then its electronic configuration is it's got electrons in s orbitals and then 3 electrons in these p orbitals. And there are 3 p orbitals which are labeled px, py, pz. And the most stable configuration is for those electrons to go in with their spins parallel. So if they do that, then the total spin is going to be equal to a half plus a half plus a half, which is 3 over 2. And so the multiplicity is going to be equal to 4. So the ground state of the nitrogen atom has a multiplicity of 3 over 2 times 2 plus 1, which is 4. And we can describe it using what we call a term symbol, in which we put the multiplicity at the top left-hand side, and then we put a symbol, which in this case is S. And this is a little bit confusing because this has got nothing to do with spin. This is related to what's called the orbital angular momentum. And I mention this because you'll come across this in the diagrams, but that doesn't really concern us at present. So let's have a look at what's going on. What we've got is we've got CH is reacting with N2. And the spin of CH is equal to a half. In other words, it's a doublet state. And the spin of nitrogen is equal to 0. 2 times 0 plus 1 is 1. It's what's called a singlet state. And so this reaction that we've got up there on this diagram, so here's CH, which is a doublet state, plus nitrogen, which is a singlet state. It's occurring on a doublet surface. In other words, it's a surface with a spin of a half. But if we look at the products that we want, which is HCN plus the nitrogen atom, then the spin of HCN is equal to 0. So in other words, it's a singlet state. The spin of nitrogen, as we said, is 3 over 2. It's a quartet state. The overall surface has got, so the overall, we've got a spin equal to 3 over 2. In other words, it's a quartet surface that we're dealing with. So this product here is occurring on this quartet surface. And if we're going to get from CH plus N2 over to HCN plus N, we've got to undergo a curve crossing in which we go from a doublet surface to a quartet surface. And that's disallowed, as we said before. It's very slow, and the calculations indicate that it doesn't really happen. And so what the main result of this Moskaleva and Lin paper was to argue that the products are going to be NCN plus H, which is occurring on a doublet surface here. Yep.
So the CH has 3 radicals, so it could be a doublet or a quartet also. Is that correct?
Yeah, but the ground state is a doublet. Okay? Yeah, there are quartet excited states, but the ground state is a doublet. I thought you were going to ask another question, which is, I've slightly pulled the wool over your eyes. Not too much, but if you look at this NCN, the ground state is actually a triplet. So the NCN has got a spin of 1, and the hydrogen atom has got a spin of a half. And we can combine these, either adding them together. So the overall spin for NCN plus H is going to be either 3 over 2 or a half. And the surface that I've shown there is the spin a half surface. So these products here are formed from this spin a half surface. Okay, I hope I haven't totally confused you. But these are very important issues as far as this particular reaction is concerned. And we need to understand that the spin of the system is really driving the way in which the reaction occurs. And the original presumption that it was HCN plus N that's formed is almost certainly incorrect. And it's that it was HCN plus N that's formed is almost certainly incorrect, and it's NCN plus H that's the product. Okay, and so this is an important slide in sort of conceptual terms, because this is the region in which shock tube studies are made. So we're relatively high temperatures, but this is the region in which NO formation occurs in certainly in low pressure flames. So the NO is being formed at these lower temperatures, and so this CH plus N2 reaction is going to be important in these regions here. And so what's at issue is the extrapolation from the high temperature data down to the regions that we're interested in here. And there are 2 separate experimental determinations up here, and also some theoretical determinations. What happens to the NCN? Well, these are the sorts of, so here's its mechanism of formation according to Moskaleva and Lin. And then it can react with O2, with OH, with O, and each of these are forming NO. So it's still a route to NO formation. And here's a reaction, H plus NCN forming HCN plus N. That's spin allowed, and that again is an important route, but leading now to HCN formation as the original mechanism had it. And these are the rates of the main routes to NO formation, some of them involving NCN, some of them involving other species. These are removal routes. These are all formation routes. This is a shock tube study subsequent to that Moskalev and Lin paper, covering the temperature range 1943 to 3543 K. CH generated from ethane argon, and acetic acid argon, and was studied in the absence of nitrogen, and then nitrogen was added to perturb the system and to see what happens to the CH. CH was detected by laser absorption, and this is the overall rate coefficient for reaction. And the experiments that I'll show you the results of show that the branching ratio for NCN is, the best value is unity. And the lowest, a conservative lower limit is 0.7. So these are direct experimental observations confirming the theory of Moskalev and Lin that NCN is the product, and demonstrating that the best value for the yield of that product is unity. So those are the experimental measurements of the rate coefficient. And this shows the way in which the perturbation experiments were carried out. First of all, here's the profile for CH with no nitrogen present at all. So this is the unperturbed CH profile. And then nitrogen was added, and the profile was perturbed. And you can do direct comparisons between these profiles. And these are the rate coefficients for the various reactions that are occurring. So this is a sort of sensitivity analysis, but looking at the rate, at what ROP means rate of production. And so here is the main route to CH formation. CH3 plus M goes to CH plus H2. And then there are these other reactions involving either CH production or CH removal, and those are significantly less important than this main route. And then adding the nitrogen, this is the rate of production of CH. Now we've got a loss of CH because of its reaction with N2. And the results from NCN, from looking at the NCN, show that its yield is very close to unity. So this is a direct experimental observation of what's going on. These are the main contributors to the kinetic scheme used to extract the rate coefficient. Okay, so that's now direct experimental observation that NCN is the key product of this reaction. This then is a more recent theoretical analysis looking at the reaction in some detail, and reasonably high level, well, pretty high level calculations. And there are basically two routes, this bold route and this dashed route, to forming NCN plus H. And here's the quartet surface. This is, as you said, quartet CH plus N plus N2. And so this is a quartet surface, which is some way above this surface here. So, we need to concentrate on this one here because the crossing from these surfaces to these surfaces over here is very slow. And what they did was to look at the mechanism in some detail. So here's that potential energy surface again. And what they did was to define paths A and B. So path A, which is the dotted one, is the full line over here. And path B is this one with this higher barrier here, again going to H plus NCN. And they demonstrated that the main route occurs on the full surface here with a little bit of a contribution from the other surface there. They then looked at the importance of the various transition states along here. And so if we imagine the reaction coming along from the left to form the products, we can imagine that the reaction flux is going to reach a certain minimum when it goes over each of these barriers here. And what we can do, or what Larry Harding and his colleagues did, was to calculate the rate if only this barrier were important, if only this barrier were important, and if only this barrier were important. And each of these rates is larger than the final rate, but it gives you an idea of which one of them is primarily determining the overall rate. And the slowest of these, which is the one that's limiting the flux primarily, is TS3, this one here. And so this is the overall estimation of the overall rate coefficient, and these are the contributions from the fluxes over these different energy barriers. And this is an analysis of the overall rate coefficient. And so these are the high temperature shock tube measurements. And you can see that the one that I showed you earlier on, the Vasudevan shock tube measurements, and the ones by Dean are giving results which are in closest agreement with the theory. So the theory is agreeing really very well with these higher values for the shock tube measurements up here, but which extrapolate to lower values for the overall rate coefficient in the region that's important in terms of prompt NOx formation. Then a couple of slides which I'll pass over very quickly, in which NCN has been detected using laser techniques in this is in a methane air nitrous oxide flame. And then this is using cavitative ring down, which I mentioned earlier on, as a way of probing for NCN. And this is in this is in another flame. There isn't the details of what the flame is there. But NCN detected directly using spectroscopic methods in combustion systems. Okay, let's move on. And now let's have a look at the second reaction, which is NH2 plus NO. And this is important in this technique called selective non-catalytic reduction, SNCR, which is used in a variety of applications in power stations, for example. And it was developed by Exxon in 1975, and it involves the addition of ammonia, which converts NO to nitrogen. And this is the overall reaction. And it occurs in this temperature regime between 1100 and 1400 K. So this is the reaction surface. It's complicated, and we'll come back to it later on. And there are two channels. There's a channel which produces stable molecules, N2 and water here. There's this high barrier channel that leads to N2O plus H2, which isn't important. But then there's this other channel which leads to N2H plus OH. And the Miller and Bowman analysis showed that the reaction has got to be self-sustaining. So it mustn't be exclusively terminating. And for this to occur, they showed that the yield of channel B must be at least 0.25 and increase to 0.3 above 1100 K. So this is a prediction that comes directly from a simulation saying that the reaction, can't go exclusively to these products, these very stable products down here, but these products here must be significant at the sort of 30% level. And so these are experimental and modeling studies of the rate coefficient and of the yield of N2H. So whole host of experimental measurements and then theoretical analyses here. Jiao and Smith, Miller and Glabborg is a prediction based on simulations of complex mechanisms. And what it shows is this increasing yield of N2H as you go to higher and higher temperatures. And here's the overall rate coefficient, which decreases as the temperature goes up. So these are experiments which were carried out in MC Lin's group, where they used pulse laser photolysis of ammonia, NO, helium mixtures using 193 nanometers. So this is an excimer laser wavelength, and total pressures in this range. And they determined the branching ratios from mass spectrometric detection. So they were using pulse laser photolysis coupled with mass spectrometry, and detecting NH2, H2O, and CO2. And they couldn't detect OH using mass spectrometry directly. It's too short-lived. So what they did was to add CO to the system and use the reaction between OH and CO to form CO2 as a means of determining the amount of OH that was there. And so this shows the profiles of water and CO2, and this is the NO decreasing. So you've got NO decreasing and the products, water and CO2, going up here. And the CO2, because of the presence of CO, is a probe of the radical channel leading to OH formation. And what they found was that alpha increases very sharply above 1,000 K, and much more sharply than Miller in his simulations would have predicted. And so this was a surprise, but they reanalyzed. So what they did was to use pulse laser photolysis, but now they use spectroscopic methods for monitoring the products. And they monitored NH2, and the NO reactant and the H2O product were monitored by mass spectrometry. So they combined mass spectrometry with direct monitoring of the NH2. And they were able to explain away their previous results and finish up with these results here, which agreed with earlier results and with the predictions of the Miller models. And so these are other experimental results. So these are shock tube studies of NH2 plus NO, measuring NH2 by absorption spectroscopy behind reflected shock waves, using this system, monomethylamine, ammonia, NO, argon, pressures around about 1 bar. And the branching ratio was determined by kinetic modeling of a detailed reaction mechanism with the branching ratio as the fitting parameter. So this was aimed primarily at measuring the branching ratio at these elevated temperatures. And this is a bit of the reaction mechanism that was used. And so this shows the system and the sensitivity analysis. So this is the sensitivity of NH2. And this sensitivity profile here is to the branching ratio. So this is the branching ratio, and this shows that the NH2 is primarily sensitive to this branching ratio here. And so these were the results that they generated, these open squares up here. This shows the sensitivity of the values, varying the values by a very small amount, a few percent, and changing the profile significantly. So this is the NH2 profile as a function of time. And so this then gives a good constraint on the way in which this branching ratio varies as you go to higher temperatures. And these are theoretical results. This is the surface that I showed you earlier on. And this is N2H plus OH. Okay? And this is the potential energy surface. So here's N2H. And this is looking at the reaction in the reverse direction. So N2H plus OH. And these very closely spaced profiles are attractive parts of the energy surface, and the more widely spaced ones are repulsive parts of the energy surface. And you can see that if the OH comes in along here, then that's an attractive approach, and similarly in these different directions here. And it's an interesting problem because the nature of the interactions are quite different, as we'll see in the next slide. So this shows, these are high-level calculations, and so this is HNNOH, so this is the complex, as a function of the distance between the N and the O. And the internal degrees of freedom of the N2H and OH fragments are fixed, so they're sending them in at a fixed angle. And the solid symbols refer to the ground state, the opal symbols to the lowest excited state. So there's the ground state, there's the excited state. And this is for a covalent interaction, and the dashed curve is for the hydrogen bonding interaction. So longer range, we have a hydrogen bonding interaction, and then, so that's coming in a particular angle of approach. And then this is the stable, this is the formation of the species for the covalent direction. So in other words, what they're doing is they're looking at this part of the potential energy surface as the OH comes in to interact with N2H. So this is telling us, giving us information on this part of the potential energy surface. And so then these are the results of their simulations of the branching ratio compared with the experimental results. And by tuning the surface, they're able to get good agreement with the experiment. Okay, so that's been a very interesting process over several years as experiment and theory have been able to resolve this issue of this significant reaction channel between NH2 and NO, which leads to the formation of this of OH, which sustains the reaction. In a way, it's slightly counterintuitive that it occurs, but clearly from both experiment and theory, it's clear that it does occur. Okay, let's now move on to the final example, which is Reburn. So this is a key approach to reducing NOx emissions from power stations. And so this is the initial combustion process. And what they do is they add fuel downstream in this so-called reburn zone, and then they add some more air to burn off that secondary fuel. And the importance of this secondary fuel is that it helps to reduce the NO, and one of the key reactions is this one, HCCO plus NO goes to these two products. So this is identified from simulations as the key reaction in Reburn. So this is the way in which that reaction is thought to occur. So these are hydrocarbons reacting in the presence of oxygen, forming oxygenated species, going eventually to CO and CO2, but at the same time generating these hydrocarbon species through, first of all, through CH3 plus CH3, forming C2H6 and C2H5, and then that then reacts through ethylene and vinyl eventually to generate acetylene. And acetylene reacts with oxygen, and this is a well-characterized reaction, to generate HCCO. And the HCCO then reacts with NO to form these species down here. There are limited measurements, good agreement at room temperature, and this is the temperature dependence, which hadn't been studied over this whole range, but this is the recommendation that was given, relatively small temperature dependence and a high rate coefficient, with an uncertainty of delta log K equal to 0.2 rising to 0.4. What about the products? So that was the overall rate coefficient. So these are discharge flow measurements using molecular beam sampling and looking at the product distributions and measuring CO and CO2 and getting a yield beta, which is Kb over Ka plus Kb of 0.23. So beta is the fractional yield of CO2. These are other measurements. These are measurements from Göttingen using photolysis together with FTIR spectroscopy, obtaining beta is equal to 0.28, the yield of CO2 equal to 0.28. And then this is excimer laser photolysis, CO and CO2 detected by infrared laser absorption, and getting a somewhat lower value of beta equal to 0.14. And this is the only really detailed theoretical analysis by Vrieken in which, so we've got the HCCO reacting with NO, and it can come out as with this, with HCNO plus CO as a product and HCN plus CO2 as a product on this sort of complex surface. And it's a pressure-independent reaction, but nevertheless you need a master equation analysis in order to sort out what's going on. And so these are the experimental results at low temperatures, giving a yield of CO2, which I'm afraid is called alpha in this case, but it's the same as the beta in the earlier diagram. The yield of round about 0.25, 0.3, and this is the theoretical prediction, the theoretical result from this analysis here. And these are earlier predictions coming from Miller's work, where the yield of this particular channel was somewhat greater. Okay, and that, yeah. So that's that. I hope what I've done is to show you that by combining good experiment with good theory, it's possible to sort out these reactions. And one of the particularly difficult things about them is that a key aspect was the nature of the products. In some cases, the products were, there was more than one product, and the yield of the different products was important. In others, it was identifying what the product was. And we're pretty good at, we're generally pretty good at measuring rate coefficients overall, but product yields is quite difficult. And one of the nice things about each of these reactions, I think, is that there's been a close interaction between theory and experiment, with theory leading in some cases and then experiment leading and so on, and good interactions between the two of them, helping us to understand the nature of the products from these reactions here. Okay, I said we'd be over relatively quickly. Are there any questions?
I'm wondering that for the final products for HCN plus CO2 or HCNO
Okay. I mean, the important thing to remember here is that this all occurs at relatively low temperatures in the reburn region. So this isn't occurring in the flame. It's occurring post the flame. And so you've got to worry about what the products of those reactions are, but it's not the same as injecting HCN into the middle of the flame itself. Yeah.
We have been talking about oxidation. So in many fuels, liquid fuels, you have additives that eliminate oxidation pollutants, right? So how does detailed chemistry take into account those additives, and how does one go about dumping from, if you have those trace additives that have significant effects in making some reactions faster and suppressing some reactions? How do you go about that process if you have dumping them next step?
Yeah. I mean, these methodologies that I've talked about here are primarily aimed at power stations. With car engines, then there are alternative approaches. One of the things that I have to apologize for, and this has been made very clear to me by one or two people, is that these talks are entirely gas phase. I haven't talked about the interaction between the gas phase and the surface. And obviously, as far as car engines are concerned, a different approach is used in which you use a catalyst to remove the NOx from the system. And so there are controls, I mean, increasingly controls in the engine, but you're using a catalyst to remove the NOx. There are, as you say, ways in which you can put additives in to the fuel system, to the combustion system itself, which can lead to NOx, to reduction in the NOx. I have to admit complete ignorance of the way in which you would do the modeling in a situation like that.
Professor, how do you evaluate the RRPM model? Do you think it's a reusable model?
Well, it all depends on what you mean by the RRKM model. Yeah, no, but I mean, the RRKM model, in essence, is a transition state model. So basically, what you're doing with RRKM is you're saying that the microcanonical rate constant is that. And so it's a statistical model, and some people argue that in some circumstances statistical models don't always work, and that's certainly true. But within the limitations of a statistical model, then it's a good approach.
High temperature region, in my opinion, in high temperature region, the planetary surface just cross each other. So that means you have manageable saddle points. So you see here that no matter the RRPM model, in fact, is beyond 2000 Kelvin. So I'm not sure this model really works fine for high temperature.
For high temperatures, so just let me get straight what you're saying. So what I think you're saying is that if you've got a potential energy surface like this, then there may be excited states that are involved in the reaction in the surface, and that may make it difficult to. Is that what you're saying? Yeah. Yeah, and that is certainly true, and you have to worry about the interactions between these potential energy surfaces. Increasingly, this is being recognized in master equation calculations in that curve crossings are being incorporated into those master equation models. It's not something that's routine, but it is increasingly possible. Ultimately, you're going to run into difficulties because as you go to higher and higher and higher energies, reactions are occurring more and more and more rapidly, and there isn't the time for the energy delocalization, which is implicit in this model. So, what's assumed in this model, the RRKM model, is that if you've got a given molecule with a given energy, then that energy is randomly distributed amongst all the modes of motion. It's got what's called ergodic behavior. And it takes time for that delocalization to occur of the order of 10 to the minus 12, 10 to the minus 13 seconds. And so if reactions are occurring more rapidly than that, then this model is going to break down. And that's going to be more and more of a problem as you go to higher and higher energies, in other words, to higher and higher temperatures. Yeah?
Could you briefly comment on these high temperature gaseous reactions where both NOx and CO are formed? This is again a bit leaning towards internal combustion, but those, so what are the factors that affect this balance between NOx and carbon monoxide?
Phew. I would find it very hard to comment without a more detailed context of that. I'm not sure I fully understand the question. Maybe we should talk about it later on and look in more detail at what you're saying.
I just kind of a general question. So you have these third body reactions, and it seems like I would think that all of the species involved have a different third body efficiency. Is there a way, is that actually something you measure, or it's something you calculate, and then how does that play into the mechanism when you develop it? Is there, you have to list each one of them?
Yeah, it's a real problem. It's clear that some molecules are more efficient at removing energy than other molecules. There has been a lot of work done on energy transfer. So if you take a vibration excited molecule in its V equals 1 state, and you collide it with helium, say, you can measure the rate at which that relaxation occurs. For a collision between such a molecule and helium, the mechanism is an impulsive one. So the molecules collide and the relaxation occurs quite inefficiently. But what we're talking about in these systems is quite different. We're looking at highly energized molecules and not a vibration-excited state which is well separated from other states. We've got high densities of states up here. So collisions can actually remove quite small amounts of energy, but do it very efficiently. So there isn't really a highly successful model which allows us to predict what's going to happen. I mentioned a paper by Jasper and Miller, which looks at energized methane colliding with a variety of species. And that's one of the best analyses, but it's a specific system and it's difficult to generalize. And so what we usually do is, if we've got experimental data, within our master equation model, we fit, using that exponential down model that I described, so we fit the parameter. And we fit the temperature dependence of the parameter. And you move to another system and you find that you need slightly different parameters, maybe slightly different temperature dependencies. It's very difficult to predict.
So you have a basically like a global third body efficiency, or is there, do you end up putting, you do this kind of analysis for each species in your?
In our experiments, we generally have a single bath gas. So we have a diluent, say argon or helium. And so we can model it for that single diluent.
And so since the concentration is much higher
than anything else, yeah. So the relaxation is determined entirely by that species.
Okay.
But obviously, in a combustion system, you've got mainly nitrogen, oxygen, and water. And those are the species you've really got to worry about. Any more questions?
Just one general question. A lot of running really contribution to let's see, the PM 2.5 particle. So recently I saw some picture about China, so I'm very surprised. So you didn't have an answer.
What NOx contributes significantly?
Lots of contribution.
Yeah.
PM 2.5.
Okay. We'll talk a little bit about this tomorrow. But what NOx, if you take a city, if you consider a city, and you look at the particulate matter within that city, then the particulate matter has got a fairly complex structure, fairly complex composition. Soot is an important contributor, but also secondary aerosol. Aerosol formed in the atmosphere is important. And there are three main sources of that secondary aerosol. One of them is sulfur dioxide, so sulfate. And that's less and less and less important as we remove more and more sulfur from fuels. Another is nitrate. So NOx gets oxidized in the atmosphere, forms nitrate, and that nitrate, or NOx gets oxidized in the atmosphere and finishes up as nitrate in aerosols. And so NOx is a very important contributor to particulate matter within a city. And the final contribution comes from organic compounds. So organic compounds, again, are oxidized in the atmosphere, and those oxidized species are incorporated into aerosols. And what I found surprising was that if you look at a city like London, then even in the center of London, a substantial fraction of that particulate matter is secondary. It's not by any means just soot. There is secondary particulate matter present, even in the center of a big city like London. Okay, so tomorrow what we'll do is we'll look at some of the consequences of combustion, and we'll talk about what goes on in the atmosphere, both in terms of general atmospheric processes, but also a little bit on climate change and a little bit on air pollution. Okay, see you tomorrow.